Hello, everyone. I think we'll just go ahead and get started. Thanks a lot for coming. This is the last session of today. I'm happy to see some of you here. Today's topic is about powering 100 million daily users. My name is Rezaul Hoque. I'm an engineering manager at Microsoft. I have been working at Microsoft for 8+ years now, and I have been one of the core team members of building Microsoft Office Graph, if you're familiar with it. Today, however, we'll be talking about another experience that I am been recently working on, and that is basically building a service which powers people experiences across Office 365. So, a show of hand, how many of you are familiar with Office 365? Actually, a lot of you. That's great. And all the people experiences that across the workloads like SharePoint, OneDrive, Outlook, OVA, are being powered by the service that we will talk about today. And this service basically has almost 100 million daily active users. Therefore, the service we have to build had to be able to scale to that limit to be able to serve all these users. So the experience kind of looks, as you can see on the screen, it's just a simple card. But like before we go on and talk about what this experience is and why we build it, we start with the core mission of Microsoft, right? So the core mission of Microsoft is to empower every person in every organization to do more. So what does that mean? It means that, like, what is productivity to you at work? It's about communication and collaboration. In Office 365, when you actually collaborate with people through different mediums, if you knew who this person is better, you would collaborate better. That's like real life. If you actually work with someone in real life and you know them better, you know what they want, what they will need in advance, then you can actually work more effectively. The purpose of this persona card is actually exactly that, to replicate that experience in an online environment. To be able to contextualize a person and create a 360 view of a person, you need a lot of data about that person. Fortunately for us, Microsoft owns a lot of data about a user working in an organization who is a Office 365 user. For example, some of that person's data is in SharePoint, some is in Skype, some is in Outlook, and then some of the public-facing data are actually in LinkedIn, right? And all we need to do is to take all this data from different data sources, aggregate those data, run some ML models just to understand what is useful. Like for a simple example, like just showing contacts and email can be very useful, but it could be even more useful if I knew this person is someone I'm going to meet like in a week in a meeting, right? And this is the document that I need to read. So this card tries to capture those scenarios and actually present it in an experience for you based on the context that you are in. Right. So to build this experience, we're going to talk about 3 big dimensions. One of them is scalability, right? How do we build a scalable architecture which can support this usage? The second thing we want to talk about is the card like appears from all this data, but if it takes seconds to come, no one is going to be productive, right? You will be unproductive trying to use the card. So it has to be like super snappy. Like as soon as you want to know about someone, all the data just needs to appear at the right time instantly. So that's one of the challenges to build for performance at this scale. We are going to talk a bit about some of the things that we did and some of the key takeaways from that experience. And lastly, when you start and do a project like this where you know this is going to grow, the number of developers working on that project also grows. Often, like how many of you started with a project which started with like 2 people and ended up more than 30 people? Yeah, like 50% of you, right? And I think this is the problem is that I think we all acknowledge that working on a code base with like 2-3 people is vastly different from working in a code base where 50 people contribute at the same time all the time, right? So we are going to talk a bit about what are the things that we did to ensure that our code base is scalable. Let's start with the first one, scalable architecture. We take a very high-level overview. This is an oversimplified view of how our architecture looks. let's say you have the experience on the right-hand side. Is it on the left-hand side? No, yeah, it's on the right-hand side. So you have the experience on the right-hand side, and you have the card on the left-hand side. And as I said, all the data exists. Let's say that we call them data services. They are different services which also Microsoft owns, like some other teams own. But we are going to build this experience. All we need to do is create another service which is going to aggregate all this data, right? And basically pull all this data, rank them, and then deliver it on time. Normally, only this would have worked. But as I said, because we need to make it very performant, a lot of these data services are actually old and legacy services, and they can be as slow as 5-6 seconds. But we need our experience to be very snappy, as less than a second, right? So all we do is that we basically cache that, right? So this is a very high-level pieces of the architecture. So when we talk about scaling our architecture, what it means, like if we just take this diagram here, like what are the high-level pieces that need scaling? So you need a bit of compute, because you build a new service. When the load increases, you need to have more compute available for you to scale. The second thing you need is, like we talked about, cache, right? Because we need to speed things up, so we want to cache things. So we need a cache resource, and that, of course, needs scaling as well. And then all the dependency services that we kind of said, oh, all the data is there. But that itself needs to also scale, right? So luckily for us, we had to work with these teams to ensure that the load we are going to put on them, that they can handle. And those are different challenges, but we were able to get a buy-in for all those services. So we're not going to talk much about that here. The other thing which is very easy these days is that, OK, you need some compute. You use one of the cloud platforms, right? You can use Azure. You can use Amazon Web Services, or any other cloud platform. Naturally, we used Azure, because Azure is great as well. But like compute these days is pretty simple, right? Like you can actually outsource the scaling of compute to your cloud provider. So you can say, I need this many instances. If the load increases, then it automatically handles this for you. So there's nothing much to talk about there. Then we are left with cache resource. So we used Redis cache. Are you familiar with Redis cache in Azure? Yeah, some of you. But normally, it's just a key-value pair cache. It's a network-attached in-memory cache, which Azure provides out of the box. It's a managed resource, so you don't have to do much. You just like consume it through the REST endpoints. So now, of course, we knew from day one that we are building it for many experiences, and we're going to cache many things. So this needs to scale as well. If you pay more to Azure and you use a premium SKU of Azure Redis cache, you have the caching, scaling functionality provided to you from Azure. So you don't have to do much if you throw money to the problem. However, that comes with X number of functionality, which we don't need. So since in our scenario, we knew that if you want to keep the cost low, this would be our bottleneck. So we don't want to use high-end SKUs, right? So we used the lowest SKU, and we did our own scaling strategy. So we're going to talk a bit about what we did to scale Redis instances. So scaling can be done in two ways, right? Vertical and horizontal. So vertical is very simple. Like you ask to get a bigger SKU, bigger machine. But there is a cap to that, right? Let's say that we are using the biggest machines that Azure is providing to us. And it's like around, I think, 50 to 60 GB per instance. So in this diagram, you can see we have like 4 instances of Redis running. So when we need to cache here, we need to somehow distribute our data across these 4 instances, for example. So let's say Eleni, a user, comes and like hovers on a card. So this piece of, like every part of the card has some piece of data which is cached. And that cached data has to end up in one of these partitions, right? So the first thing is that each piece of data, you have to give it a unique ID, right? So let's say that it's a cache ID. The way we form it is that we actually use the accessing user ID, accessing user's ID, and target user's ID, and a tenant name. So you form a unique key. But then what you do is that you basically take that unique key that you want to partition you want to keep that data across these 4 instances. You have to choose which bucket you want to keep it, right? So we do a consistent hashing of the key. and then we do a modulus of the number of instances you have, right? So that way, you basically end up in a bucket. The thing to note here is because it's a one-way hash and it's the same hash function, if you have the same key, you'll get the same hash value. And then you do a modulus of the number of instances that you have, you will reach to the same bucket. So if you store it once, you can come back to it again, right? So this is a very standard technique. Now, let's say like you have spread this across all these instances, your data. Naturally, one of the questions is that who ensures that the data is distributed properly? And the hash function has property which basically ensures that your hash keys are bucketed across this uniformly, right? So that's why we use a hash function. If you made your own like random stuff, then it could be that one of the instances could have filled up more than the others. Now, let's say that the experience grows and you cache, and now all these 4 instances are almost getting full. So what do, right? You go ahead and just add one more instance. But now let's play through what happens right now. Let's say that like I went to Azure, I clicked, I got a new instance, I went and updated my code and said, hey, I have 5 instances now. So the same user came, the data is cached in the bucket 1, if you remember from the previous example. Then I ask for the data again. The service basically looks at the same cache key, which is the same cache key, and then you do a constant hashing with the same hash function. Then you get the same number. But this time, instead of doing a modulus of 4, you have changed the code to the modulus of 5. And therefore, it can end up in some other bucket, right? It could, by probability, end up in the same bucket, but that's by chance. So one of the nice things is that we do not go and wipe the entire data, because we say, if it's able to come to the same bucket, then you still have a cache hit. And Redis basically has a property that if it gets filled, and then there's new data coming, it will not reject it. It's going to take it in. It's going to drop the oldest TTL values, right? So that's kind of a nice property to use. So in our case, let's say in this example, it ended up in bucket 4. And of course, it's a cache miss because that value doesn't exist there, so you have to repopulate it. The thing to note here is, if you want to build a scaling strategy as such, you have to be tolerant to loss. In our experience, when this happens, when we go and scale it up and add more instances, we get cache misses. And therefore, because our experience can withstand it, and the way it withstands it is that it takes a performance hit, right? So it's not super fast, but then it goes to the downstream services, calls it, populates the cache, and serves the result. So it doesn't block. So this is interesting and also very important to note if you want to use a scaling strategy as such. You can use the same strategy for your partitioning of your any kind of data, even if it's persistent. But in those cases, when you cannot tolerate loss, you have to go and repartition the data. When you added the 5th instance, you have to like redistribute your data. You have to have a strategy to actually be able to do that, which is slightly a harder problem. Okay, now we kind of like talked about compute, Redis, and the data services, and we scale each of them, right? And then let's say that like you have all these resources that we just talked about, and they individually scale, right? So that's nice. And then like you say that, oh, these are all my resources. I'm going to host it in one of the data centers, right? For example, in here, I host it in North Central US. But the way to scale now is that you can replicate this entire thing again and again in different data centers, right? So you just like nicely package it, and then you do more of this. There are a couple of reasons why you would want to do that. It's not just that you want to scale this way. This basically gives you a disaster recovery scenario. For example, if one of the data centers goes down, right, your traffic, like if you have a traffic manager on top, it just distributes the data to the other data centers. Last year, Azure, one of the data centers in Azure basically went down. I don't know how many of you, okay, someone is nodding their head. Maybe you were affected. Were you affected? Yeah, okay. So we had an experience which was not affected because of this setup, right? So our like load just like went to other data centers. They individually scaled inside. We saw a blip in our optics, but were not affected. So this is a very nice thing to have. But it comes with a cost, right? If all your users are in the same place and you have another data center you're maintaining, it is some overhead, but it depends. It is better to be ready for that scenario than not to be. Azure basically published a very detailed RCA on why that has happened. It's really nice because it was a lightning strike, and then the entire data center eventually went down. Like you would imagine, it has a lot of safe wires. Like it has safety nets. Like it's not like that if something trips and it just goes down. All data centers have, like Amazon has it as well. But still, these kind of things happen with human errors and natural disasters. So I would really encourage people, even if you build a small service and you actually serving production traffic, you don't want to be down. For that, you need to have high availability. Therefore, scale your resources and then ensure at least you have one or at least two or more data centers that you are in. Then the next thing is that you are in one geography. Right? Let's say that you are in US. And then you can do the same thing in other geographies, right? So you can just scale it in a geography level. So it's like pretty simple, and then you put a traffic manager on top of everything. The thing to note here is that you don't do it just because you are scaling it out or you want to have disaster recovery. One of the main reasons why you want to do it is that you want to be closer to your users. For example, if I have a lot of users who are connecting from Europe, maybe they are US users. Let's say they work in Shipstead here. How many of you work in Shipstead? Because I saw some people from Shipstead. OK, let's say any Norwegian company, but you're traveling a lot, right? So your account is hosted in Norway. So we know that you are Norwegian as a user, so you are supposed to be in Norway, but you're connecting always from India because you're traveling, right? So those calls are going to come all the way, right? And that's going to affect your performance. But if we had a data center in India, right? So then you would connect to India, your cache will be in India. If you move around, your cache will move around with you. So therefore, the performance it will help your performance, user experience. You'll have a better user experience. You'll be more productive. Therefore, we meet our mission and goal in Microsoft. Right. This is a very nice overview of all the places Azure actually has a data center today. It's a bit old, like a year. I'm guessing they have a bit more now. For us, what we do is that we look at this overview, and we have another chart which basically shows where all our users are connecting from. Based on these two, we kind of decide where are the places that we want to have data center presence. And this is also one of the key takeaways, is just don't build everywhere Azure has data centers, right? Because there is a cognitive overhead, even if they are exactly the same replicas. For your developers, there is a cost of maintaining them, going in Azure, looking at these resources, provisioning them, and so forth. The best thing to do is optimize for where your users are, because that's where you will get the best benefits. Right. So we kind of talked a bit about scaling our architecture, and but then we also said, okay, caching is helping in our performance, but let's look at how it actually helps in our performance. So from day one, we were very bent on saying that we have to design for performance. We cannot be slow. When you start with performance, I think the first thing to ask is, what is performance for you? Right? You cannot just say, oh, we want to be super blazing fast. That's what we initially said. We want to have a blazing fast person card. But what does that really mean? Right? So you have to really define that scenario for yourself. For example, a very simple example I often use is that when you go and read a news, right, you basically don't need all the data for all the news. All you need is all the titles, because the first thing as a user you do is you gloss through the titles, you triage it, and then you decide to click on one. And there is a few milliseconds within which you can do a lot of smartness for your end user. You can predict and prefetch the right ones. So we do something similar. So we have defined it that if anyone clicks on someone or hovers on a person, as long as we can show the top part of the card super fast, the user will feel that he has started understanding who this person is. And we have defined that the rest part of the card, which is more harder to produce, can come slightly later, right? And we have given ourselves some goals. So we said that the top part of the card should be rendered in 250 milliseconds from the time you click, which is an insane requirement, but still, we kind of believe that it's doable, right? Let's see if it is doable. And then the rest part of the card cannot just wait forever as well, because most probably you will consume it in half a second, the top part of the card, and then immediately when you want to consume more, the data should be there. So we have given ourselves like around 600 milliseconds to render the rest part of the card. And then you scroll more, and then you have more time to render more stuff. So let's see how we can power this experience. Let's say we have this high-level overview architecture. A user comes in. Let's say the top part of the card, the data we want, so it sends a request to our service. And the service kind of looks at the cache and says, it's not there. It's the first time, right? So it goes to the rounds in service, takes seconds, comes back, renders the top part of the card, then renders the rest. It is more than like 6 seconds, I think, if you are to do it like that. So it's kind of what we have achieved now is that, OK, you click, you get the card in 6 seconds. But if you click again, then it's super fast. But then no one clicks for the second time because the first time was so slow, right? Yeah, natural problems. So we do something which we call prefetch and cache. It's a very standard technique. It's not anything sci-fi. What you need to optimize here is that before the user click comes, you want to pre-populate the cache. So in one of our experiences, for example, Outlook, right? It's a mail scenario. So every scenario, we try to understand what the user is trying to do in that scenario. When you go and open your emails, not all of you go and immediately click on, hey, I want to see who this person is. Most probably, the first thing you do is that you look at your emails, you look at who mailed you, or you want to craft a mail, so you actually ask for someone's name. So it so happens that from telemetry, we know that you have around like 2-3 seconds before you go and do the first click on to understand anyone, right? So we kind of leverage that insight, and we kind of, as soon as the page is rendered and you have these people on the page, we identify all the people in the page, and we send a prefetch signal to our service saying that, hey, go and get ready for the top part of the card, right? So that when the user clicks and the call comes, you get a cache hit. And that is how we are able to also render the experience very quickly from the first click onwards. And then this strategy just continues. For example, you get the card, and the card itself has more people rendered in it. So you might click to know more of that person. So you do the same thing. You just send it and hope that before you have clicked it, we have prefetched it for you. So I just want to go back a bit and say that even though it works really good, it has a huge drawback. Who can say what the drawback is? Any guesses? Yes?
A lot of unused data that you might not actually go.
Yeah, absolutely. As you mentioned, there is a lot of data that we prefetch that no one might click, right? So from telemetry, I can just tell you, on average, we have around 30 to 40 people rendered on one page if you go to an email. And on average, maybe 3 of them are clicked. So most of this data that we prefetch, just to be insanely fast, is gone to waste. So what we did is that we started using machine learning models, where instead of just saying that we are going to prefetch for all these people, we tried to start predicting your behavior and what are the people that you might go and click, right? So if we can actually predict better on who are these 3 people that you might click, then we will just prefetch those 3 people. And for example, just to get an idea of what this means in plain term, so let's say that we divide users into different buckets. There is a bucket of users that you interact very often with. There can be a bucket of users who are completely strangers. And then there may be a bucket of users who are strangers, but you have upcoming collaboration with, you might have a meeting with for the first time, or you're meeting after a really long time, right? So those are indications that you might really be interested to know about this person. And then we run these ML models, just try to predict how your behavior is, and that's how we can actually optimize what we prefetch and cache. So then so the way we try to do is that we try to actually keep the cache hit ratio the same while prefetching less, right? So this is a work in progress, but one takeaway from this is that even it's okay to start very simple and dumb, get your users on board, see that you're successful, see that the usage is good and people actually want this experience, and then go ahead and do smartness like this to actually reduce your cost. All right, let's move on. So now it's all good and dandy, right? So you have the middle tier service. Let's say that you have everything on cached, right? We have done prefetch and cache. So now we need the top part of the card. So we do a simple GET request to our service and say, hey, like give me this data. You get a cache hit, let's say, right? Reading from the Redis cache is like single-digit millisecond, so it's like almost no time. Remember that the top part of the card was 250 milliseconds, right? So when we try this experiment, like we are trying to measure, we see that it takes 600 milliseconds almost in some regions. So it's not in all regions, but in some regions, actually more than half of our regions, which are like in developing countries around the world, where the networks are not great, even a single HTTPS request takes more than 600 milliseconds just to go and come back. So that doesn't meet our goal at all, right, the top part of the card. So the first question is, why does it take so much of time? So naturally, if you do an HTTPS, you have a three-way handshake, TLS, back and forth. And if it's a spotty network, it takes more time. And needless to say, there are monsters on the internet, right? Like everyone knows that. Yeah. And they are cute as well. So, but it doesn't help in my performance. So naturally, like what we need to do is we have to somehow like get rid of this TLS handshake once, upfront before the user clicks, right? Like the same strategy like the prefetch. Like when the user comes, all these things should be done in advance. So one could go and say, hey, like it's 2019, use HTTP 2.0, right? Like that's exactly what it's built for. And actually it works great. But I guess you guys were thinking that, right? Yes, some nodding heads. But the thing is that if you look at worldwide traffic, only 40% of the traffic worldwide actually has HTTP 2.0, because not all browsers are up to date. Especially in corporations, a lot of use old standard browsers. That includes Internet Explorer as well. So, yes. But the thing is that you cannot always rely on technology which is good, because your users are really behind, even if it's 2019. So for us, we knew that we are going to have to build a tunnel in advance, create that tunnel, and then use that tunnel continuously. So we had two options. We could use Websockets, or we could use SignalR. How many of you are familiar with SignalR? Oh, wow. It seems like a .NET conference here. Everyone uses SignalR. But so there is no need for me to say how awesome SignalR is. But for short, for people who haven't used it, it's just a duplex channel that behind the scenes, it of course uses WebSockets, keeps it open, but it does more than that, right? Like it kind of keeps connections open to multiple clients, and it resends them, retries them. It does polling behind the scenes. It has a lot of nice goodness in it. So we kind of looked at it and say, okay, we could use WebSockets, or we could use SignalR. The API looks very easy to use in SignalR, so we just use SignalR, right, for simplicity. Kind of did the same call through a SignalR. Just for completeness, the SignalR also does an HTTPS request upfront to establish the connection, but that is done a long time before the user clicks, so that cost is gone. And then once the user clicks and then the request goes through SignalR, you get to the service has everything cached, and then you measure, and it's 230 milliseconds. So plus a single-digit millisecond on the reading from the cache. So we're going to meet our goal. At this point, feeling really cool, right? Like you are able to scale. You are meeting your performance goal. You have done all this SignalR thingy. Super nice. Life is good. We're going to roll forward. We are around 1 million daily users now. Things are working very good. Every day you come, you have your coffee, you feel good about yourself. And now everyone says, okay, let's go more, right? And in my head, it was like, okay, if we can serve 1 million, then we have weeded out all our issues. So it's smooth riding from here. So we kind of started, we want to go to 70 million, because at that point we knew that we had 70 million daily active users. So we kind of say, okay, we scale up, right? So Azure, basically, we throw some money to the problem. We get some more compute as the users roll in. And we onboard more and more organizations into Office 365 organizations, or tenants, if you're familiar with it, right? And then we started seeing something really weird. Some of the CPUs started becoming hot, and they would crash and burn, but there was no explanation. It's like we have a load balancer and everything. The traffic is being distributed nicely. So we thought at least, but if you restart one of these machines, another one gets hot, and then that also crashes and burns. burns, right? So we kind of like had to not have our coffee that day and really investigate what the hell was happening. So remember this thing that we use SignalR and we thought, oh, life is so cool? It so turns out that when you use SignalR, you need, because it keeps backplane and it has to retry, you need to configure IP affinity. And that's also okay, right? Like what IP affinity means is that the same IP, you want to end up in the same backend server because you have some state there. But it should be okay. But apparently, when we did more investigation, it turned out that these big organizations want to really be safe and secure, so they have their firewalls and NAT, and then they use one public-facing IP. So all the users basically end up being the same guy. And then it just comes to the same VM. Even though we have a lot of VM, when we onboarded new organizations which were bigger, naturally we onboarded the smaller ones first, right? But then when we started onboarding bigger tenants in Office 365, we started seeing this. Kind of like the takeaway from this for me, and I think what I want to like get at is that every resource that you use, right, when you build your architecture, needs to be scalable to your needs. Like we use SignalR, and SignalR, if you read about SignalR, which is true, is a very scalable solution, right? But it does not scale to our scenario because we have a different scenario. Like we have this unique need for not having the affinity on our backend servers, right? So we had to like go and use a WebSocket, finally. But then at this time of the project, it was also problematic because we had like almost I think 5 million daily active users. Things were really becoming hot. So a lot of PMs, product managers came and said, oh, I want to try this out. I want to try this out. So it was like pulling a lot of features, right, already while we were rolling out. That meant that we had a huge communication stack, right, like lots of features exposed. You want to rewrite the communication stack? That's like the worst. How many of you have had to rewrite your communication stack to some other protocol? Not many. You guys are lucky. So at this point, we had to do that. And we had an option between WebSockets or REST. We knew that REST doesn't cut it. But at this point, there was, I just want to share some very interesting. So they had this thing that in some browsers, like Safari, and if you're on a Mac, the REST performance was really great, right? So that was strange. But the hypothesis there is that people who have Mac, like I do also, and using Safari, they are most probably sitting in a developed country with a really good network. So it's not about the machine, it's about where you are. But also the other thing about WebSockets is that it's just raw WebSockets. So you will actually, there will be failures. There will be times where you cannot connect. So if you cannot connect, then you don't have any experience, right? So we needed to support REST as well. So what does that mean for us? That now we have to support both. We have to rewrite our communication stack to support both. So instead of doing that, what we did, what we call is REST over WebSockets. So we created like 2 layers on both sides. The client always sends REST requests. The layer basically converts that into a WebSocket frame. It goes through the tunnel, and then it unpacks as a REST request and replays it as a REST request on our server side. And then that kind of worked really good. Yes. That brings me to my third topic. Let me see how we are doing on time. Yes, I think we are good on time. Yes, right. You're good on time, yes. So brings my third topic. As you scale, that naturally means that you have more users. That's why you're scaling resources. You don't do it for fun. And you have a good performance. But with that also means that you are tempted and naturally to experiment more features. So your code base grows. And the number of developers working on that code base grows. When we started, it was like 2 people or 3, right? Or 2 of them were actually coding. Now we have actively 50+ people working on that project. So there are many ways to actually solve that problem from day one. Like one common approach is to use microservices, right? Like you fragment your domain up front. You have this nice smaller services, so the people work only on those services. So that's one way to scale your code base. That's in my mind. But you can also use monoliths, of course. In monoliths, like you have this layered architecture where you have view, model, controller, right? And then, as I said, on the other hand, you have microservices. The thing is that there is a cost associated upfront on creating microservices when you have two developers, right? Let's say that you go for 7, 8 months, and then you're like, if you look at our experience in the card, you have sections. So it's a very well-suited architecture. You could say that every section is powered by a small microservice. It's like domain, is a bounded context. So it fits really nice. But still, we didn't go ahead and do it because we knew that there was a lot of overhead in doing that. So what we did is that we did something which we call organized monolith. What it means is that you have a monolith, but instead of having this layered architecture inside code, you structure your code to actually have this good features of a microservice, except the fact that you cannot deploy independently or you cannot scale independently. You scale as one unit, but internally you structure your code to be more domain-driven, right? And I think I like to call it organized monolith because you basically think that at some point you want to do microservices, so you kind of get ready for that world. If you look at our architecture, every section is powered by one of these blocks, right? So, like, for example, the contact section is powered by the context provider service. It's not really a service, but it's one of those domain blocks where you have in C#, you have a C# project, it's a library, and it only deals about that domain. And then it goes and does whatever is needed. It owns its own data and so forth. So just to iterate like some high-level concepts is formed based on bounded context, similar to microservices. It's simple and small, right? That's one of the key. And one of the main things is that it owns a particular set of data. So if it owns a particular set of data, if someone else needs that data to add, view, edit, whatever, it has to go through this block. Very similar to how microservices work, right? And in this world, one of the most important things is to not have type dependency on each other, right? Because if you have these small libraries, and then they like have type dependency on each other, then you have formed a spaghetti. Maybe layered architecture would have been even better. So then how do they actually use each other? So you basically extract all the interfaces out, and then you actually communicate through that. Right, so there are many ways to do this. One way is what I just said. And then, or else if you are familiar with the mediator pattern in C#, you can actually implement that as well. So it's basically ensuring when you have these blocks, there is a mediator which handles these dependencies for you. Because later on what you can do is that you can extract one of these, put a webhead on top, and then make sure that instead of talking to the interface, you're talking to the REST endpoint, right? Then it becomes your microservice. For example, like, you have this organized model, you can take it out. As I said, you can build a small service. But given we have started with an organized monolith, we didn't have to take the upfront cost of building a service. But then when we needed to, we actually are ready for that world. Our code is structured that way. And we actually started doing that. Now we have like spin 2 more services out of it, at least 2. And then there are also like new services which starts being a new service from day 1. And then you start forming this microservice architecture for your application. That's so. Before I end, high-level takeaways. Scaling architecture. For your overall architecture to be scalable, every resource that you use, you should identify it up front and ensure that it scales for your scenario. Then you can only truly say that you have a scalable architecture. So designing for performance, to me, means a lot about understanding your scenario. So it's not about like some of the techniques that we used. If you understand your scenario and you have enough optics to understand where your bottlenecks are, you will figure out what's the best way to achieve performance for your scenario. So Peter Drucker basically has this quote where he says, if you can't measure it, you can't improve it. This really sums up what designing for performance really means, at least for me. And lastly, scaling engineering. It should be considered as a first-class problem. Not many people reflect at it upfront. And even if they do, often they kind of like jump into microservices. And I think there is a wall in between as well. So think through your scenarios and see if starting with an organized monolith could be a better fit for your scenario. That's all I had for today. Thank you so much for coming. And I can take some questions if there are any. Yes, please.
I didn't quite get the rest with WebSocket.
Yeah, I can explain again.
WebSocket?
Yes, so let's say that you are on the JavaScript side, you just have another library. So through that library, you send your REST request, right? That basically changes, packs the REST request into a WebSocket frame, and then just sends it back.
So it's not like WebSocket connection does not work and you switch to REST.
You can do that as well. So our layer basically allows you to do, so when you write, so the beauty of that is that you as a JavaScript developer will only, I will go back so that I can see you. So what you do is that you send REST requests, but you send it through our library. The library basically converts that into a, packs it into a frame and then sends it. Let's say that this layer was not able to be formed, right? Then instead of packing it into a frame, it just sends it as a REST request. So we are allowing both. So as a front-end developer, you don't have to worry about whether it goes through REST or WebSocket or HTTP 2.0. It seamlessly is taken care for you. Yeah? That doesn't answer your question? Yeah, cool. Yes?
Can you tell again about the problem with SignalR and why WebSocket doesn't have that problem?
Yes. So SignalR basically uses WebSocket behind the scenes and, of course, TCP. But SignalR also keeps bookkeeping on the backend side. It has a backplane because it has to resend some. Because what it does is that it creates multiple connections. So it's great at resending the messages to all clients and bookkeeping of who has received and who has not. These are not functionality that WebSocket has. WebSocket is just raw, right? Yeah. More questions? Yeah. If not, thank you and enjoy the rest of the day.